In 1970, the town of Yungay rested peacefully in a Peruvian valley. Above it loomed Mount Huascarán, a towering peak that had safely overseen the region for millions of years. Then, an earthquake shook the region. In an instant, the mountainside collapsed, sending millions of tons of rock and soil rushing downhill. Faster than a speeding train, the resulting debris flow buried the entire town, killing around 20,000 people. Something as massive and permanent as a mountain can turn into a deadly river of rock and mud with almost zero warning. To understand why, we have to look at the hidden physical forces acting beneath our feet. A landslide is, at its core, Earth moving down a slope driven by one relentless force: gravity. Gravity is constantly pulling material downward. What keeps our landscapes intact are resisting forces pushing back: rock strength, soil friction, and stabilizing plant roots. This is an incredibly fragile balance. The moment those forces are weakened, gravity wins and the slope fails. You don't need to live near towering remote peaks to be at risk. Everyday features like gentle hillsides, steep winding riverbanks, and man-made slopes fail constantly. Because gravity never stops pulling, this invisible battle creates a constant worldwide threat, requiring us to pay close attention to the exact ground we build on. Think of a slope like stacking books on a highly tilted table. As long as friction holds, the books stay put. But if you add water to a hillside, it acts exactly like spilling oil on that table. It kills the friction. At a microscopic level, heavy rainfall floods the ground, filling spaces between soil particles. This intense pore water pressure pushes dirt apart from the inside, drastically increasing the hillside's weight and forcing particles to lose contact, causing internal friction to zero out. Once friction is gone, the earth moves. Depending on the soil composition and the slope angle, this movement can take the form of an earth flow that slowly creeps for decades, bending trees along the way, or it can manifest as a violent rock avalanche, tearing down a mountain at over 300 kilometers per hour. Recognizing the specific trigger and the local geology determines whether a community is dealing with a minor road closure or a mass casualty event. Extreme weather events generate immense volumes of water, turning dry soil into highly fluid mudflows. In Venezuela, the extreme rainfall of the 1999 Vargas tragedy generated destructive flows that buried entire communities. Even after the earth settles, previously failed slopes remain highly unstable, historical scars. The 2014 Oso landslide in the United States demonstrated how these old slide zones stay lethal for decades. The danger rarely ends when the dirt stops moving. Large slides often block rivers, creating temporary natural dams. When these volatile blockages inevitably break, they release massive downstream flash floods. This cascading sequence of landslides and severe flooding was responsible for immense destruction and thousands of lost lives during India's 2013 Kedarnath disaster. The Indian subcontinent faces a unique level of exposure. The Himalayas are geologically young and actively rising from tectonic plate collisions, leaving them packed with steep, heavily fractured terrain. Combine those volatile slopes with intense monsoon rainfall and rapid human infrastructure development, and the region reaches a breaking point, resulting in devastating events like the 2024 Wayanad landslides. As populations expand deeper into these active, steep environments, normal geologic processes are colliding with human settlement, resulting in heavy casualties. Scientists now monitor these danger zones from space. In 3D terrain maps like this one, they use high-resolution LiDAR and satellite radar to detect millimeter-scale ground movements long before a visible crack ever forms. When these early warning networks flag an unstable hillside, geotechnical engineers intervene to artificially boost the slope's natural resisting forces. They construct retaining walls to physically hold back soil, drive deep steel rock bolts to pin fractured outer layers into solid bedrock, and install drainage systems that act as release valves for dangerous internal water pressure. When slopes do fail, the economic toll is massive. Clearing blocked supply chains, rebuilding highway infrastructure, and stabilizing the resulting ruins requires immense logistical effort and heavy machinery. These advanced tools prove we have options. By manipulating the physical equation of gravity and friction, we can actively hold back the mountains. On an individual level, survival relies on immediate action. Watch for new cracks appearing in walls or the ground. Never try to cross an active debris flow, and always run sideways to escape the immediate path of a slide. In vulnerable regions, heavy, continuous rainfall is the clearest natural warning system you will get. When the soil reaches maximum saturation, evacuation orders must be followed immediately. Looking ahead, continuous satellite data and artificial intelligence are allowing scientists to build predictive digital twins of volatile mountainsides, calculating exactly when a slope will give way. We cannot switch off the relentless downward pull of gravity, but by understanding the mechanics of how the Earth moves, we can build smarter, evacuate faster, and save communities from our planet's fastest-moving hazard.